Welcome to this explainer. Today, we are taking a seriously fascinating micro to macro journey into one of the most complex and honestly most powerful engineering marvels on the planet. We're going to look at how we capture invisible subatomic forces to literally light up entire cities.
Okay, I want you to start by picturing a number in your head, 88. Specifically, 88 tons of coal. Just imagine this massive, towering, incredibly heavy pile of traditional fossil fuel. Think about the sheer volume of that, right? The heavy transport you need, the huge physical footprint required just to keep a power grid running for a bit.
Now get ready for a completely mind-blowing shift in scale. A single, tiny uranium-235 pellet, literally the exact size of a coin you probably have sitting in your pocket right now, holds the exact same amount of energy as that entire 88-ton pile of coal. It is just a breathtaking example of the almost unimaginably dense power locked away right inside an atom's core.
But that staggering reality brings us to the core question of today's explainer. How do we safely harness that microscopic potential? How do we transform it into the electricity that powers our modern lives without, causing a total disaster?
Well, the answer lies way back in a massive 1938 breakthrough that basically changed the entire trajectory of the world. Scientists Lise Meitner and Otto Hahn discovered nuclear fission. What they figured out was that the nucleus of a uranium atom can actually split into smaller parts. And when it does, it releases a tremendous amount of invisible heat and energy. That one single finding revealed that the atom held a power capable of completely revolutionizing global energy forever. So to actually harness this safely, the whole process has to be built up incredibly meticulously, step by step. It starts with those tiny, coin-sized pellets. We take them and seal them inside these highly durable 50-centimeter metal tubes made from a special zirconium alloy. This stuff is designed specifically to survive extreme heat and resist corrosion. These tubes become our fuel rods, which are then bundled together in perfect alignment and finally lowered right into the reactor core, the true beating heart of the whole plant.
And when all those tiny bundles come together, the macro scale of this operation is just wild. Take Canada's massive Bruce power plant on Lake Huron, for example. The place is huge, covering an area equal to over 1,000 football fields. Its 8 Candy reactors churn out a staggering 6,400 megawatts. To put that into perspective, that is enough to supply 30% of all the electricity used in Ontario, from one tiny pellet to lighting up millions of homes.
But before any of that massive energy starts flowing, the core is treated like an absolute, highly restricted fortress. It is locked behind 2 solid meters of reinforced concrete. And why so much security? Well, because once that core goes active, the intense radiation would release invisible heat capable of delivering a lethal dose to anyone nearby in literal seconds. So yeah, that heavy concrete makes it crystal clear that this is no place for casual visitors.
So while the reactor is fully shut down, perfectly clean and safe, operators in these bulky protective suits go to work. With absolute surgical precision, they load exactly 5,760 of those fuel rods into the core's 480 tubes. Now, interestingly enough, at this pre-activation stage, the fuel actually emits radiation so incredibly low you can barely detect it. It lets the operators position everything perfectly, kind of like setting up the pieces of a giant silent machine, just waiting to be woken up.
Okay, so once the real show actually begins, things get wild. Highly unstable uranium atoms get disturbed, say by a particle striking them. They enter this excited state and suddenly fire off extremely fast, invisible neutrons, basically like tiny subatomic bullets shooting out in every direction. These neutrons tear right through those zirconium walls until they slam into another uranium atom. That atom splits, releasing an enormous amount of heat, and fires off even more neutrons. It sets off this cascading, exponential multiplication of massive energy.
Now, because of that exponential growth, the absolute most crucial thing here is control. Starting a reaction is one thing, but if it runs out of control, the heat exceeds safety limits and literally melts the internal components. It's the most feared scenario in the nuclear world, a core meltdown. To prevent that runaway train scenario, plants use a remarkably clever system. Control rods made of materials like boron or cadmium. When these are inserted into the core with millimeter precision, they basically act like sponges, absorbing those flying neutrons and slowing down the reaction. Without those breaks, you've got a major problem.
With everything safely regulated from a central control room by highly trained technicians, that massive heat from the core is used to warm up a closed circuit of water. But here is an absolutely fascinating detail. This water is kept under such extreme pressure that it transports the core's heat at nearly 300 degrees Celsius, but it never actually boils. No boiling whatsoever. It's a completely sealed loop, definitely not for drinking, and its only job is to quickly move all that intense heat away from the core.
Deep inside that watery, incredibly high-pressure environment, something visually stunning and honestly a bit eerie happens. The entire core is bathed in this brilliant, glowing blue light. It's called the Cherenkov effect. Basically, it happens when charged particles actually travel faster than the speed of light within that specific medium of water. It is this beautiful, ghostly visual reminder of the extreme atomic physics going on just beneath the surface.
Alright, so that superheated water from the core transfers its thermal energy to a second, totally separate circuit of water. This time, the water is allowed to boil into dense, extremely high-pressure steam. And that steam blasts its way straight into the turbine hall. Imagine a colossal, sprawling structure, literally 400 meters long and towering 20 stories into the air. The scale shifts drastically here. We've gone from the invisible, microscopic atom straight into the massive, roaring machinery of heavy industry.
That extremely dense, fast-moving steam slams into massive turbine blades with just unbelievable force. It whips them around at a blistering 1,800 revolutions per minute. As these giant turbines spin, they're converting all that thermal energy into mechanical energy, driving massive electric generators that ultimately push out 750 megawatts per reactor. That's exactly enough juice to power the daily lives of 500,000 people.
Now, once the steam has done its massive job turning those giant turbines, it doesn't just go to waste. It gets channeled into a condenser, where it's rapidly cooled down, usually using cold water pulled from nearby lakes, rivers, or those massive sweeping cooling towers you always see in pictures. The steam condenses right back into liquid water, fully ready to endlessly repeat this majestic cycle of energy creation over and over again.
However, we do have to talk about a very serious challenge: the aftermath. After about a year or so inside the core, the uranium fuel rods are basically spent. They can't keep the reaction going anymore, but they remain incredibly hot and highly dangerously radioactive. You can't just toss them out. They have to be submerged into massive cooling pools that are over 8 meters deep, filled with completely crystal clear water. And that water is amazing. It acts as both a crucial heat absorber and an impenetrable shield against the radiation.
And here's the thing. They have to sit in there for at least a decade. Right now, today, over 500,000 of these used fuel rods are resting silently at the bottom of these deep pools all over the world, just waiting, patiently, for their temperatures and radiation levels to finally drop down to a point where they are safe enough to handle and pack away for long-term storage.
Which really leaves us to ponder one final huge question. We've just seen this breathtaking journey, right? From a single coin-sized pellet all the way to generating enough immense emission-free power to run entire cities. But how do we weigh the absolute marvel of this incredibly dense energy against the heavy, decade-long responsibility of safely managing its radioactive waste? It is a fascinating, delicate balance between unparalleled engineering and a profound long-term legacy. Thank you so much for joining me on this explainer. Keep asking questions and keep exploring this incredible world around us.